Now let's spend some time with the tougher concept, which is lipid transport. We'll explore this graph here in detail in just a little bit, but for now I just wanted to give you the big picture. We should now start off with some basic concepts. Because fat and cholesterol are hydrophobic, meaning they don't easily dissolve in blood, they're going to require carrier molecules to enter and move throughout the circulation. Fat from the diet and from the liver are going to associate with amphiphilic proteins called apolipoproteins, which act as a structural protein and surface marker. Together with other lipids, including cholesterol, cholesterol esters, triglycerides, and phospholipids, these apolipoproteins are going to form lipoproteins. What are the different lipoproteins that we need to cover? Well, these different lipoproteins include our VLDL, IDL, LDL, and HDL. I'll get to those, but first let's start with some easier enzymes. There are several key enzymes used in lipid transport. Pancreatic lipase is going to degrade dietary triglycerides in the small intestine, and specifically it's going to cleave triglycerides at the 1 and 3 position, giving rise to free fatty acids and a monoacyl glycerol. So here we see a triglyceride that meets its pancreatic lipase enzyme, which is going to degrade it into these long hydrocarbon tails, which are the free fatty acids. These free fatty acids can then enter the enterocyte and reesterify into a triglyceride, so that it can be exported in a chylomicron. Another enzyme is going to be lipoprotein lipase, or LPL, and this is found in vascular endothelium in adipose and muscle cells, and it's going to catalyze the exact same reaction as pancreatic lipase in the gut. It's going to degrade triglycerides that are circulating in chylomicrons and VLDL so that they can be absorbed by cells locally, and the chylomicrons then go on to become remnants that are transported back to the liver. Hepatic triglyceride lipase, or HL, is going to degrade triglycerides in IDL to form LDL. So let's go ahead and look at our chart here. We have an IDL molecule. It's going to meet its hepatic triglyceride lipase, and it'll then form an LDL while liberating some fatty acids in the process. And then lastly, our hormone-sensitive lipase is an intracellular enzyme which degrades triglycerides, mostly in adipose cells. Do you remember what the function of our LCAT enzyme was with regards to cholesterol? Well, as I mentioned a moment ago, LCAT, or lecithin cholesterol acyltransferase, is going to esterify cholesterol, which means it allows that cholesterol to enter the core of a lipoprotein where it can get stored for transport. About 2/3 of cholesterol is going to be in the circulation in an esterified form. This enzyme is also required to get cholesterol into HDL to make a mature HDL molecule. HDL that is not loaded with cholesterol is going to travel to the liver, meet with this LCAT enzyme, and load up on cholesterol. So here our loaded HDL can take two paths. It can go back to the liver, effectively reducing the amount of cholesterol systemically, or it can transfer cholesterol esters to other lipoproteins. CETP, or cholesterol ester transfer protein, is the enzyme that mediates the transfer of cholesterol esters to these other lipoproteins such as our VLDL, IDL, or LDL. The apolipoproteins are amphipathic proteins that are going to bind to lipids to form lipoproteins, so that these lipids can then be carried throughout the circulatory and lymphatic systems. Do you remember what being amphipathic means? Amphipathic means being both hydrophilic and lipophilic at the same time. Therefore, these apolipoproteins can float in the bloodstream while still attracting lipids as well. There are going to be 5 most important and most tested apolipoproteins that we need to know. Apolipoprotein E is going to mediate remnant reuptake from the liver. This is going to be found in VLDL, IDL, HDL, chylomicrons, and their remnants. When these lipoproteins are pooped out and depleted, they can return home to the liver by apolipoprotein E. Just remember that ApoE is found in every lipoprotein except for LDL, so you can see it's not in LDL down here. Apolipoprotein A1 is going to activate the enzyme LCAT, which is mostly found in HDL molecules. Since our LCAT converts cholesterol to cholesterol esters in HDL molecules, it makes sense that ApoA1 is found on the HDL lipoproteins. Apolipoprotein C2 is a cofactor, required for lipoprotein lipase, which is going to be used to degrade triglycerides in VLDL and chylomicrons. As we'll see in a minute, chylomicrons and VLDL molecules are loaded with triglycerides. So if they express this ApoC, they can find the LDL on vascular endothelium to unload some of their triglyceride cargo. Apolipoprotein B48 is going to mediate chylomicron secretion, so this is only going to be found on chylomicrons and the remnants. Our last major apolipoprotein is B100, and it's mostly present on VLDL, LDL, and IDL molecules. It functions to bind the LDL receptors and allows these lipoproteins to unload their products to cells in the body. LDL molecules are typically loaded with bad cholesterol molecules, so ApoB100 isn't always the best. If you want to be 100 years old someday, hopefully you don't express a lot of ApoB100 markers on lipoproteins. Now that we have shown what makes up each of the various lipoproteins, let's go ahead and talk about what these lipoproteins do. How are they classified? Well, the different lipoproteins are named according to their density. From low to high density, we have chylomicrons, VLDL, IDL, LDL, and then HDL. In general, the higher density implies more cholesterol and proteins, less triglycerides, and a smaller size. Therefore, chylomicrons and VLDL molecules would have lots of triglycerides and less cholesterol, while on the other hand, LDL and HDL would have more cholesterol and less triglycerides. We'll start by talking about where chylomicrons come from. Let's pretend that we eat a really fatty meal. That fat is going to make its way to the gut, get broken down into triglycerides, and enter enterocytes. The dietary lipids in enterocytes then enter the cell's endoplasmic reticulum, where they co-assemble with a freshly translated large apolipoprotein, which is ApoB48. This can then become a chylomicron, which also contains ApoC2 and ApoE. From the intestine, chylomicrons enter the lymph system and go through the thoracic duct before reaching the bloodstream. What is the main function of a chylomicron? Well, the main role of chylomicrons is to deliver dietary triglycerides to peripheral tissues. Chylomicrons contain mostly triglycerides and only a small amount of cholesterol. So let's go ahead and look back at the structure here. A lot of triglycerides, very small amount of cholesterol, which is the C. So the chylomicrons are going to meet lipoprotein lipase in the bloodstream, which is going to release the triglycerides. So we see that down here. The triglycerides can then get fed into muscle tissues or adipocytes. Once they've delivered most of the triglycerides to other tissues, what remains is now termed a chylomicron remnant, which transports its remaining cholesterol back to the liver. We just saw how triglycerides are going to travel from our gut to the body. So now let's take a look at the liver. VLDL, found here on our graph, is going to be secreted by the liver, and it can drop its contents off to peripheral tissues. That brings up the question, how do VLDL and chylomicrons differ? Although VLDL still has more triglycerides than cholesterol, it has a higher cholesterol content than chylomicrons do. Another important distinction is that VLDL is produced in the liver, whereas chylomicrons are produced in the intestine. However, VLDL and chylomicrons have a similar function, which is again to deliver triglycerides to peripheral tissues. After they've delivered some triglycerides, this VLDL molecule is now going to be called an intermediate density lipoprotein, or IDL. Although IDL can be taken up back to the liver, it often gets further degraded, loses its ApoE, and becomes an LDL. Do you remember what apolipoprotein marker is found on our LDL lipoprotein? Like many things in life, LDL isn't inherently bad. In fact, without it, you'd be in serious trouble. It's just bad if you have too much of it. If found in excess, LDL may be thought of as bad or lousy lipoproteins. This is because it gets transported from the liver to the rest of the body and dumps off a lot of cholesterol in the process. In large arteries, LDL can get oxidized and trapped in the vessel intima. Oxidation of this LDL causes macrophages to recognize it as a pathogen, so they'll endocytose it and become foam cells, which is the beginning of atherosclerosis. You'll hear more about atherosclerosis in the cardiovascular section, but just realize that high LDL levels contribute to the formation of an atherosclerotic plaque. Our last lipoprotein to talk about is HDL, which can be thought of as good cholesterol, thus the smiley face. Remember that a high HDL is healthy. High HDL is healthy, an alliteration right there. This is because HDL basically has the reverse function of LDL, since it's going to transport peripheral cholesterol, including that in the atherosclerotic plaques, back to the liver. HDL is going to be produced in both the liver and the intestine. When HDL is created, its core is mostly empty, but its membrane has a lot of proteins, which give it a high density. As it travels through the circulation, it's going to pick up cholesterol from the body, causing it to fill up and expand until it ends its journey back at the liver. Once the cholesterol gets dropped off at the liver, it can then be sent to the intestines as bile salts. So notice how we have bile salts here, which then get dropped off in the intestine and excreted in the body. So this HDL cholesterol can either be sent in as bile salts or it can get repackaged into VLDL molecules and sent back to the body. Which apolipoproteins are found in the HDL molecules? Well, HDL acts as a repository for apolipoprotein C and E, which are needed for chylomicron and VLDL metabolism. So let's quickly test our knowledge. What organs take up low-density lipoproteins, or LDL lipoproteins, from the circulation? And what receptors are used for this? The answer is the liver and peripheral tissues both have receptors to uptake LDL from the circulation. This receptor is specifically going to be your LDL receptor, which recognizes the B100 apolipoprotein, which is found on our LDL molecule. Let's talk about the things that can go wrong with lipids and lipoproteins. A standard lipid profile measures LDL, HDL, total cholesterol, and triglycerides. A dyslipidemia is any significant difference from normal values in our lipid profile. A high LDL and a low HDL are both well-established risk factors for atherosclerosis and coronary artery disease. Before we move on, I think it's critical that you understand lipoproteins. Do you remember which was the good cholesterol and which was the bad cholesterol? Well, hopefully you remember that a high HDL is going to be considered good or protective because it moves cholesterol from the body back to the liver to be excreted as bile salts. A high LDL is bad because it may lead to atherosclerosis formation. Okay, so let's talk about some hyperlipoproteinemias. Type 1 dyslipidemia, also known as hyperchylomicronemia, is defined as an increase in chylomicron levels. This results in elevated levels of triglyceride and cholesterol in the blood, although it mostly just affects triglycerides. Hyperchylomicronemia is caused by an autosomal recessive defect in lipoprotein lipase, or a defective ApoC2, which is the cofactor needed for that lipoprotein lipase. How can hyperchylomicronemia present clinically? This can result in pancreatitis, hepatosplenomegaly, and xanthomas. So you can see an example of a xanthoma tendinosum here in the picture. You can see those on the fingers there. It's important to note that hyperchylomicronemia does not increase the risk of atherosclerosis, since there's not going to be high levels of LDL present. Type 2A dyslipidemia is known as familial hypercholesterolemia, and it's characterized by an increased level of LDL and cholesterol. It's caused by an autosomal dominant mutation that results in the absence or a deficient LDL receptor. Without LDL receptors, LDL cannot be uptaken by tissues, and therefore that LDL is going to accumulate in the bloodstream, eventually being deposited in the walls of vessels. LDL carries cholesterol back to the body, from the liver to the body, so cholesterol is going to be increased as well. This is going to lead to atherosclerosis and vessel injury, such as the one shown here in our picture. This can also cause tendon xanthomas and also corneal arcus, which is the pale arc of cholesterol that you can see in these pictures. These deposits generally begin at the top and or bottom of the iris and fill in until they cover the whole circumference. There is also a thin, clear section separating it from the sclera. Type 4 dyslipidemia, or hypertriglyceridemia, is also an autosomal dominant disorder. So we've had autosomal recessive, autosomal dominant, and autosomal dominant. So this hypertriglyceridemia is autosomal dominant and is characterized by a high hepatic production of VLDL molecules. Do you remember what the VLDL molecules are primarily made of? VLDL contains mostly triglycerides, so you'll see an increased triglyceride level on a lipid profile. This most notably causes acute episodes of pancreatitis. So that's all for the hyperlipoproteinemias. Here we have a 35-year-old woman who has an MI. On exam, she has an Achilles xanthoma. What is the defect and blood work of her findings? Well, this one's a trickier one. You're going to have to kind of extrapolate. This woman typically has a type 2 familial dyslipidemia, which is also termed hypercholesterolemia. This disease results in absent LDL receptors, so LDL and cholesterol are increased in the bloodstream. This high LDL will then cause atherosclerosis, which contributed to her heart attack, while her high cholesterol levels can be seen in the Achilles xanthoma. Since the patient has a heart condition, MI, and xanthoma formation, it can be assumed that they have high cholesterol levels, which are the trademark of our type 2A dyslipidemia.